Hey everyone, just want to go over the rules for voltage drop according to the Canadian Electrical Code. We're going to look at 8102. I got 4 examples we'll go through, but first I'll just kind of go over a couple of these rules that we'll focus on, specifically sub-rules 1 and 3 for our purposes. And then we'll also look at appendix and appendix B and appendix D. Okay, so let's get going at this. All right, voltage drop. Rule 8102. Voltage drop in an installation shall be based on the connected load of the feeder or branch circuit if known. Okay, so right off the bat, when you know the load, that's what you're going to use. And I have a few examples that will use that first part of that statement. So when you know the load, that's what your voltage drop will be based on. But if we continue reading, otherwise, it shall be based on 80% of the rating of the overload or overcurrent device protecting the branch circuit or feeder. Okay, so if we don't know the load, if the load's not given to you, then you're going to use a load which is basically 80% of the overcurrent device protecting that circuit. Where would you do that? Very simple. Just think of a receptacle. We don't know what the load is going to be in that receptacle at any given time. It could be 5 amps one time, it could be 10 amps the next time, we don't know. So in that case, that's where we just take, for example, say a 15 amp overcurrent device protecting some plugs. We would just have our load as 12 amps, right? It's 80% of 15. Okay. How much voltage drop are we allowed in a circuit? If we continue reading sub-rule 1, we're allowed 3% in a feeder or branch circuit and 5% from the supply side of the consumer service to the point of utilization. Okay? So on my questions, I tell you specifically the maximum voltage drop that will be permitted. If I do not state that, then according to the code, in a feeder or branch circuit, we're allowed 3%. The remaining 2% is for the service side, more or less. Okay? For everyone that's watching too, you may hear me referring to you guys a lot. These videos I make for my students who I teach, but it's for everyone, other licensed people, other apprentices, wherever you may be in Canada. But what this channel is not meant for is for the do-it-yourself handyman. Okay, this stuff here is for licensed contractors, licensed electricians, and apprentices who are learning to become that. Okay, so this page is not intended for to be used, or for it's welcome for everyone to learn from, but unless you are a licensed electrician, you should not be doing this work. It's actually illegal here in Ontario. You need to hire a licensed electrical contractor to be doing any kind of installation. Okay. All right, so let's get past that. Let's do some examples here. But before I do that, that was sub-rule 1. So when we're doing voltage drop calculations, we need to know the load. And if we don't know the load, then it's based on 80% of the overcurrent device protecting that part of the circuit. All right. I want to also read off number 3, sub-rule 3. So notwithstanding sub-rule 1, wiring for general use branch circuits rated at not more than 120 volts or 20 amps in a dwelling unit. And what's a dwelling unit? Well, you'll have to go look that up in definitions, section 0 of the Canadian Electrical Code. But when you have a circuit that is no more than 120 volt or 20 amp in a dwelling unit, with the insulated conductor length measured from the supply side of the consumer service to the furthest point of utilization, you can use what is called table 68, right? And let's go look at it. It's pretty quick, right? It's a big title. You can read that. But table 68 is basically no calculation. The only thing with this table is it's for 120 volt single phase circuits with an ambient temperature of 30 degrees, and it's basically for general branch circuits. Okay, I'll talk a little bit more about that in a second, but this table basically you have 3 conductor sizes, 14 gauge up to number 10. You have 2 overcurrent devices, either 15 amp or 20, And then below that, you have the maximum length in meters that you can go with that conductor, that 2 conductor. Say like an NMD90, a 14.2. So on a 14.2 NMD90 protected by a 15 amp breaker for general purpose branch circuits in a dwelling unit, 38 meters, no calculation, done. Using number 12, go 60 meters. Number 10, 96. If your overcurrent protection is 20 amp, well, you're not going to have a selection for 14 because you're not allowed to put a 20 amp breaker on a 14 gauge wire, according to 14104. But if you are using number 12, you can go 50 meters, and if you're using number 10, you can go 78 meters on a 20 amp protected circuit. All right, so that's table 68, really handy. I have one example that will show you that. And then we have, well, I should add to table 68. So that's for general purpose branch circuits. If we go to the appendix B on this rule, in here it tells you what does not qualify for the use of this table. And what does not qualify is, or not intended for, table 68 is not intended for household appliances such as refrigerators, washing machines, central vacs, and other receptacles as per rule 26.654. You can go look that up, see what that's about. It's not the intent of this video. So if you're curious, just go look it up. Table 68 is also not to be used for your kitchen receptacles. Again, you can go look that rule up. Table 68 is not to be used for electrical heating and cooking appliances. And table 68 is not to be used for receptacles installed in dwelling units that are dedicated to medical devices. Okay, so those are the restrictions. Other than that, general branch circuit in a dwelling unit, table 68 all day long. Okay, let's do some examples. Oh, first, sorry, appendix D3. All right, so D3, we're going to reference this a few times in our 4 examples. At least 3 of the 4. Yeah, very simple to use. So table D3 is basically distance to center distribution for a 1% drop in voltage on a 120 volt 2 conductor copper circuit. Okay. And what we got on the left here is we have some various currents or some loads that may be imposed on the conductor, right? Along the top we have various gauges of copper conductor, so 18 gauge all the way up to 4/0. And then below that we have the maximum distance in meter at 1% that you can go with a given load on a given size wire. So for example, if you had a 4 amp load and you're using a 14 gauge wire, well, you can go 15.3 meters at 1%. Okay. There's a D3 continued. It's a distance correction factor. Quickly, I'll just show you on the left, you got whatever insulation you're using. You got the temperature rating of that insulation. And then we have a bunch of distance correction factor values, which I'm going to explain in more detail when we get to the point that we need to use this. Okay, so let's just do our, let's just get right at the calculations, our examples here. So I'm just going to go back and keep these rules off to the side so you can see what I'm referencing. And we'll just run with that. Okay, get my pen going here. Example 1. So it's always good to kind of pick out some key information in your questions. So I'll highlight what's important in these rules. So we have a 240 volt circuit. Has a maximum voltage drop at 2%. So in this one, I am specifying that you're only allowed a 2% max drop. All right, we're allowed 3 if it's not stated. Circuit will be wired with 10-2 AC90. And on that 10-2 is a 23 amp load. Okay. The question is, what is the maximum distance that the 10-2 AC90 can be installed? All right. And in here, we're just going to keep it simple for this one. We're going to terminate the 90-degree seat equipment, just to keep it simple. Okay, so how do we solve this bad boy? Simple. Our first step is we need to determine how far we can go at 1% with the load that was given to us, which is 23 amps. So to find that, we go to our appendix D3. All right. So appendix D3. I know I have a load of 23 amps, so if I go down the various loads, you're going to see that we don't have 23. So when you don't have a load that's stated in here, always round up. So we're going to round up to 25. So I got 25. I'm using a number 10, so I can just scroll over in this row until I get to the 10 gauge column, and I can see that at 1% I can go 6.2 meters. So I'm going to write that down, just keep it off to the side. Okay? First step is done. We took our load of 23 amps and our gauge that we're using and just lined the two up to get our 6.2. Where'd we go here? 25 right here, 6.2. Next step is what we do. What we do is we call it a distance correction factor. I'm just going to put DCF for short, but that means distance correction factor. That is going to end up pointing us back to appendix D3 continued. So that little chart that was after the D3. But how we calculate this is basically we take our load and we divide it by the rating of the conductor that's being used. And all we're doing is finding out how much capacity of that wire are we using, what percentage, right? So I know the load. Well, the load's 23 amps. I'm using a number 10, so we got to go find out the rating, how much a number 10 can handle. So we're using copper. So I'm going to go to table 2. It's going to bounce around here. Table 2, we're using 90-degree equipment, so we can use the 90-degree column. You can see that 40 amps is what a number 10 is rated for. So if I take 23 divided by 40, you are going to get 58%, basically. Okay. What we do with that, though, you're going to see is we got to round it up to 60%, and I'll show you why. So I'm going to bounce over to D3 again and go to the continued. The percent of allowable ampacity, these values up here, right? There is no 58%. So we need to round up. So we round up to 60. So I'm using 90-degree insulation temperature rating. I'm just going to scroll over till I get to my 60 column, and I can see that I will need to have a distance correction factor of 1.04. Okay, that's it for that. There's only one more step to solve this one, to find out the maximum distance we're allowed to go. So third step is just to calculate. So how do we calculate this? I'm going to write you the formula. We're going to take our max distance at 1% times our max voltage drop times our distance correction factor times the circuit voltage over 120. That's it. That's our formula. So we just plug in our numbers that we gathered from our first couple steps. So our max distance at 1%, we found that it was 6.2. We're only allowed a 2% voltage drop in this circuit. We determined that 1.04 is our distance correction factor, and we're going to multiply our circuit voltage of 240 divided by 120, which is basically 2. But we do all that, and we can see that we are permitted to go 25.8 meters. All right, done. That's it. That's all there is to that one. If our circuit if our circuit was 120 volt, then where it has 240, we'd just be 120 over 120. It's basically in half, right? So half the voltage, and basically you'd only be able to go 12.8 meters. Okay, but that's all there is to this. Now I'm going to show you some. If you ever lose this video or you get a question and you just totally forget how to do this, and you have a copy of the Canadian Electrical Code, well, if you look at Subrule 9 here, they give you an example as well. Right? So in here they say we're using number 12, and MD90 has 16 amps. Now find the max distance, right? In this case, at 3%, it'd be 38 meters. Right? And they're just stating here, if you had to go further, then you just go up a wire size. Right? So if you ever don't have reference to the video, but you have a reference to the code book and you need to do a voltage drop, well, there's an example right in Appendix D. Okay? And it's that simple. Okay, question 2. Again, I'm just going to highlight some key information out of this. So we have a 15 amp, 120 volt circuit for a receptacle. The receptacle is general purpose. It's on a general purpose branch circuit, really should say. But that's what it is, general purpose. And it's in a dwelling unit. Maybe you can see where this is going already. What is the maximum distance that a 14.2 NMD90 can be installed? Well, remember that table 68? This one here, I don't have to do any crazy calculation, right? This one here, because it's a general purpose, and like I said, this should just say more or less a branch circuit. General purpose branch circuit in a dwelling unit. The rules state that, and I'll just go back to it so you can see it. I'm going to bounce around here. Give me a second. 8102 basically says in subrule 3 that notwithstanding what basically the calculation we just did, if it's a general use branch circuit rated not more than 120 volt or 20 amps, I can just go to table 68 and get my max distance. So in this case, it's a 15 amp protected circuit because I got a 15 amp receptacle and I'm using 14 gauge wire. Therefore, I can go, I'm going to use a different color on this. Actually, I'll keep it red. Table 68 tells me I can go 38 meters. Done. Nothing left to do. That's the answer to the question. Now, if you were to work this out like we did in the previous question, you can see we can't even go close to that. And the reasoning is generally on a branch circuit and dwelling unit, you got 12 plugs on a circuit. Not all 12 plugs are fully loaded up, right? So they allow you to go a little bit further with the conductor, just for that very reason. It's the circuit's generally not loaded up to the max. Okay, so that's example 2. Example 3. Okay, I'm gonna go back to 8102 just so you can keep the rule in front of you. All right, this one here, you got a 20 amp, 120 volt receptacle. What's the maximum distance that you can go with a 12.2 AC90? This one I do note that we're terminating to 75 degrees C equipment. Okay, this is not that bad. So remember subrule 1, where it says all this voltage drop is based on a known load. Well, we don't know the known load here. It's a receptacle. I don't know what's plugged in from day to day. So subrule 1 continues on to say if you don't have the known load, then you're going to base your known load on 80% of the rating of the overload or overcurrent device protecting that circuit. So just for simplicity's sake, we got a 20 amp receptacle, so we're just going to assume it's on a 20 amp breaker. Could it be on a 15 amp breaker? It could, but that typically does not happen, right? So 20 amp receptacle is on a 20 amp overcurrent device. Okay? And because we don't know what is going to be on there, we need to use 80% of that. So 20 times 0.8 will give you 16 amps. This is the value that we're going to use for our voltage drop calculation. Okay? So really that's your first step. Find out what value you're going to use. Second step, we're going to go to D3. Okay? Appendix D, D3. I know that my current is 16 amps, and we just happen to have that as an option. Again, if it wasn't there, you just round up to the next one. 16 amps, I'm using a 12 gauge conductor. So I just scroll over and I can see 6.1. All right, so we need that number. Done. Third step. Now we got to do our distance correction factor. Okay, and that's basically taking what percentage or what capacity are we using of this conductor. Right, so I know we're going to use 16 amps, right? So I'm going to take my 16 amp load and divide it into the actual rating of this conductor, this 12 gauge conductor. So if I go back, table 2, the only difference here is, yes, I'm using 90 degree rated conductor, but because we're terminating to 75 degree equipment, I have to use this column. So in here, I can see a number 12 is good for 25 amps. Right, so I'm going to take 16 divided by 25. I divide that, I will get 64%. Again, there is no 64% option, so this will end up going to 70%. I take that to my D3 continued to get my distance correction factor, which will equal, let's go check it out, 70%. Again, we have to base everything off 75. So 75, we're going to see that our distance correction factor is going to be 1.03. Now we have all our values that we need to figure out the answer to this question. Okay, our max distance. Let's kind of scroll up here, do the last step. Same formula, just plug in the numbers. So I know I can go 6.1. Now, I didn't specify a maximum voltage drop. 8102 says we're allowed maximum 3% on our branch circuit. So I'm going to go times 3, times my distance correction factor, times, and what did I say the volt, is it 120? Yeah, it's 120. So basically 120 over 120, which is 1. But that's your formula. You calculate all this out, and you'll get an answer of 18.85 meters. That's your answer. That's how far you can go with this circuit. Okay, so that's question 3. Simple. Last one. All right, set up parking lot lights. Let me get my highlighter up here. Parking lot lights installed 45 meters from the closest distribution panel. So we're going to be 45 meters. That's a lot of highlighting. Let me back it up. So 45 meters. The lighting circuit will have a total wattage of 13.5 kilowatts, and the voltage that it works off of is 347. The question is, what is the minimum size T90 required for this distance? Also note 75 degree equipment. Now, it's up to you. Sometimes it's nice to draw this stuff out, just get a visual, what we're working with. You know, I'm a visual guy. So, you know, I got a distribution panel somewhere in the building. It is 347, 600 volt panel, 75 degree C terminals. What else? That's it for the panel, I guess. We're going to go to some lights. I'm not going to get into buried conduit or anything. Just I know I'm going out to light, and I just said we're going to use T90. All right, T90, and it's going out to light, out in the parking lot somewhere. How's that? Okay, so I'm asking, what size T90 for this light? And obviously there's more, but the total load is 13.5 kilowatts. Right, that's our load. Right. What's the minimum size wire? And what's going to be curious too, and I guess we'll do this as a second part, we'll see, well, how far can we go with that wire that we selected? Is it within the 45 meters? Right. So again, with voltage drop, you need to know the amperage. Right. So our first step in here, calculate the amps. Right? You should know Ohm's law by now. Right? So basically, current equals P divided by E. Plug in your numbers, 13,500 divided by the voltage, and you should get 39 amps. Now we know our load. Okay? So 39 amps. Second step, we got to go select the conductor, because that's really what the question was. Select our conductor. So it's T90, it's copper, right? Don't worry about any ambient temperatures or bundles of wires in the same pipe. Just keep it simple. So 39 amps. We need to select a conductor. We're going to go to table 2 to figure that out. Bounce around for, oh, right here we got hyperlink. So table 2, again, yes, we're using 90 degree insulation, but our equipment's 75 degree rated, so we're going to use that column. 39 amps, well, it looks like we are going to use a number 8. All right, well, that kind of answers the question, but again, is that number 8 good enough for 45 meters? I don't know, let's do a voltage drop calculation and see if it falls within that. Okay, so we know we're using number 8. Cool. I'll switch this up so this equals the number 8. That's what you would use in this case. But let's do the voltage drop and see if we're within range. Okay, so 3. Let's do verify. I'll just say verify distance is okay. All right, and we're at 45 meters. Okay, so we know our load. We know the size of wire. That's all we need to do, because we're going to go to appendix D3, and we're going to see appendix D3. Our load is 39 amps. We don't have an exact load of 39 amps as an option, so we will use the 40. And we're using an 8 gauge wire, so we can see 8 gauge is good for 6.2. All right, so 6.2 is our, I don't like that 6, or 6.2 at 1%. So we can go 6.2 meters on it with 39 amps on it, number 8 at 1% drop. Okay, next, DCF. Let's do our distance correction factor. Let's go figure out what that's going to be. Okay, so we know our load is 39. We're going to divide it into the rating of the number 8, which I believe is 50 amps. Was there a shortcut? Yeah, 50 amps. All right, so 39 divided by 50. If I do that, you should get 78%. And we do not have that option under the D3 continued, so this will go up to 80%. Okay. We go back to this table. Under the 80% column, 75-degree row, we can have a distance. We can see we have a distance correction factor of 1. All right, there, done. Now we just do the calculation, which we should be good at now. So 5, calculate. Let's see if we are within range. So we can go 6.2. We're allowed 3% drop. We have a distance correction factor of 1 and voltage of 347 over 120. There's our calculation. You work all that out, you'll get 53.8 meters. So we're good. We're good. Number 8's are good for this installation. But I don't know what. Say this was 65 meters or 60 meters even, whatever. Maybe 70 meters. Then if it was 70 meters, then this would not be good enough. Number 8s would not be large enough, right? We wouldn't have enough, would be too much resistance in the wire, right? So what do you do now? Well, easy. I'm just going to switch pens. Let's go, let's pretend that the installation is 70 meters. So what if is 75 meters? Well, if it was 75 meters, this number 8 is no longer capable because we're only allowed to go 53. So basically you just do it again. Just try it again. So I'm going to go, I'll just put step 1 in this for this color. Appendix D3. Right, because we know the load, it's still 39 amps. Still 39 amps. But a number 8's not good enough, so now we're going to try with the number 6. All right, we're going to try it with the number 6, the next size up. Okay, so if I go to this table here, still using 40 because there is no 39, but now I'm going to come over to number 6 gauge, which gives me 9.8. So with the number 6, I can go 9.8 meters with a 39 amp load at 1% drop. Okay, second step, distance correction factor. And what I want to say about this is this sometimes may not change, but you're not going to know unless you do it. So make sure you do this step over again, right? Sometimes it will change the DCF correction factor, sometimes it will not. The only way to know is to actually do it. So same idea, we know the load is 39 amps. We're going to divide that into the rating of now a number 6. So I'll go back to table 2. 75 degree. A number 6 is good for 65 amps. All right, so if I calculate that, calculator here, 39 divided by 65 gives me 60. So we're using 60% of this wire, basically. So that's good because we actually have a 60 degree column in the D3 continued. All right, so now I can get my distance correction factor, 75 degree row, 60. So look, it did change the distance correction factor. We now have a distance correction factor of 1.06. Once we have that, we just recalculate. So calculate new max distance, I guess. Let's say. Okay, and just plug in our numbers that we got. So with number 6s, we can go 9.8 meters. We're allowed 3% drop. We have a new distance correction factor, and the voltage is still 347. So when you work this out, you should get 9.8 times 3 times 1.06 times 347 over 120. 90 meters. So that would work. So yeah, if this installation was actually 75, well, then we'd have to use a number 6. Cool. So I hope that clears up any confusion with voltage drop. And I hope for everyone else that maybe you just learned something new with the Canadian Electrical Code and how we calculate our voltage drop up here. Other than that, if you have any questions, just shoot me a comment and I'll try and answer them. And look for more videos coming out soon. All right? Cheers.